golden angle today. I know I haven't done a phi video yet for the series, which I intend to do, so we're kind of skipping over some things to start here, but I came across this in a study. I saw a guy kind of demonstrate this, so I did a quick study of my own, and I kind of found something interesting, so I thought I would go ahead and explain that here, but it has to do with the golden angle. So those not familiar with the golden angle, it's what we're doing is you're starting with the square root of 5 is the basis for phi, right? And then you're going to add 1 and divide by 2 to get our 1.618. That's our number for growth. That is phi. Now we use 360 degrees is the common use for the circle. Where that comes from, it's unknown. It seems like it's almost given for people to use this breakdown of the circle in degrees. But if we were to break our circle up and divide it by phi, we see that we come down to 222.5 degrees right here. And if we're going to look at the difference between our total minus this, we're going to get our 137.5, which would be the same as dividing this number by phi again, right? Oops. Messed that up there. Right? So we get this 137.5 number. So what you find in nature is that when these plants grow, they grow to maximize the amount of sunlight that all the leaves are going to be able to draw in off of a stem. And so it does this in a structured way. So each branch will grow, you find, grows this 137.5 degrees off of the preceding one. So this guy had done a study where you're gonna start from 0, your first stem on the branch, and then your second stem would be 137.5 degrees from that. Then we'll grab our third stem, another 137.5 degrees, and then our fourth stem, and our fifth. And you see you get this sort of, it's not like a symmetrical pattern, but you continue to add these leaves as you're going around. And you saw that we crossed over the circle, the 360 degree mark on the fourth one right here. So if you're going to start, we're starting 0, and then we're going to say it equals, we're adding 137.5 plus 137.5. Right, now we're going to carry this down several spaces here. And you see, once we get past 360 degrees, we're going to have to see how far past we went. And then we can copy that down. And you see we hit our next lap is going to happen right here, and so on and so forth. But you see, like, we're 52.5 degrees past on the fourth. On the fifth, we're 190 degrees past, so on and so forth. So I took the actual the number that we actually get here, and then I just multiplied it out, all the multiples, and then I looked at all the laps to see when exactly you hit on 0 degrees as you're coming around here again. And I built this big table, and I'll show you a pattern that I ended up with. Is you see that when you hit these laps, you see that you're 52.5 degrees past this way, and then your next Fibonacci number, you're 32.5 degrees short, and then you're 20 degrees past. Now, just for those that maybe aren't familiar with the Fibonacci in Lucas numbers, just know that you're going to grow a series of numbers. So you start with 2 integers, and any 2 integers you start with, you're going to end up with phi. It doesn't matter what 2 you start with, but the first way that you can to grow a number sequence is going to be starting with the number 1, and then either have a 0 interval, right? Start 1 1, or you can start 0 1 or 1 0. It really doesn't matter, but you'll start 1 0 or 1 1, and we're going to add these 2 together, and then you just continue to. You're just going to copy that and draw it down, and you'll see how you continue to grow that number sequence to these very familiar numbers that we get. Now for the Lucas sequence, it would be the same ordeal here, but instead of starting 1 1, you're going to start 2 1, or actually 1 3, because your starting interval would be 2 here, and your starting interval would be 0 here. So some people add the 0 for the Fibonacci sequence here, and some people do the 2 with the Lucas sequence, but however you want to do it. So starting 1 1 and 1 3, and you'll see that you generally count these starting with the 1 right here. So 1, we'll count these down. And so, for instance, our 7th Fibonacci number is 13, and it's relative to the Lucas number of 29. And these are going to be related to each other by the square root of 5. So if you were to take this number times the square root of 5, you'd get the corresponding Lucas number. And the Lucas number is also going to be relative to the multiples of phi. So if you were to take phi here, paste the value there, and then we're going to take and say that this is going to equal phi times itself to get phi squared, and then we're going to do the same thing and just add this through and carry it down to get all your multiples of phi right here. And you'll see how this starts to become, it's a harmonic, so you never actually hit the number. There's a correction for that we can cover in another video, but you see how you're getting to the Lucas number, right? 18, 29, 47, 76, so on and so forth. And now we can, if we were to take the square root of 5 and carry this all the way down, we could, obviously we could divide these across. Equals this number divided by square root of 5. And you see how we're going to get the Fibonacci, our base Fibonacci numbers here. So too easy right there. But now we're going to look at actually multiplying these Lucas numbers by the square root of 5 again, because that's the numbers that are going to be showing up in this pattern right here. So we're going to go and take our Lucas number and then multiply that by the square root of 5. Copy this down just so we can see. And so, for instance, our first number, 52, or where are we at? 105.04565. So that's obviously right here. Now, so what that ends up being is, our remainder is 52.5, but we can multiply that by 2, and then you'll see that we're a multiple of phi to the 8th power times the square root of 5 is going to give us that number. So it's interesting that you're hitting, right? You're using this golden angle and counting the number of times you're using the golden angle to make these laps. And so for each lap that you're making around, how far you're off, you're the closest on your Fibonacci numbers. So it counts for the number of times you're counting the golden angle, and then you're gonna fall on the the actual lap is going to be, this is going to be a Fibonacci number over here too. So 8 times counting the golden angle here, you're going to get within 20 degrees, and that's going to be 3 laps around, right? And then 13 times counting the golden angle, and it's going to be 5 laps around, and so on and so forth. So you'll see all of these, they're all just basically 2, right? 21 is relative to 8, 13 is relative to 5, and so on and so forth. But yeah, I thought that was interesting. I built this big table out just to see where it, right, where it's going to actually hit, that the branch is going to be right over top of itself, and you get closer and closer to 0 as you go down. So I built this table out all the way out over here, and you get to see 30, counting it 34 times is going to be your 13 laps. That's phi to the 3rd power times the square root of 5 divided by 2 is going to be, that's how many degrees you're off. And so phi squared times the square root of 5 all the way to phi times the square root of 5, right? 3.618. You're short that much. That's the 89th counting, 34th lap. And it happens on the 144th counting of the golden angle is where you're, in the 55th lap around is where you're going to hit, you're going to be off, you're going to be past 1/2 of the square root of 5. So how close to the square root of 5 is that? We can multiply this by itself and see that we're, you know, we're off by what? 1/10,000th, close to 5, right? So we're getting dialed in. So that's your break point. That, you know, you've been multiplying multiples of phi, exponents of phi times the square root of 5 to get close to that number. Well, the next one down, so you hit some interesting numbers in here. 161 is obviously the midway point between 72 and 360 in your degrees of a circle. So 72 times the square root of 5 is 161. 161 times the square root of 5 is 360. You get this same middle value with 153 in the square root of 3. So, you know, 153 and 265 is kind of similar to what you get here, but that's for another day to talk about. So 233, you'll see when we get it in the encampment series, is going to be relative to those appointed numbers that were given for Israel as they march out. So all the tribes together, you'll see that 233 is going to be pivotal. This is kind of what got me down looking at studying phi to begin with, is going to be this number in the Fibonacci numbers, because 233 being the 13th Fibonacci number, it's the 89th lap, and you're within, right? You're getting dialed in, you know, further and further down to 0. But yeah, this is the square root of 5 divided by phi to get to this number. And then we're going to go all the way out to, you know, 322 Lucas number. So you see that number shows up as kind of interesting here. 322 shows up in the first census. That's Manasseh's number. That's Lucas number relative to 144. And then 377, right? We're at the 377th counting of the golden angle, 144th lap. And we come up to this value here. If we double that, you know, if we're pattern follow suit, we're the square root of 5 divided by phi squared. Of course, we can just test this out. We'll see if we'll call this equal to the square root of 5. And then we're going to find phi. It's this plus 1 equals this divided by 2. All right, and now we're going to say, okay, equals the square root of 5 divided by phi. We're going to get there 1.382, and then divide by phi again. And we see we're at 0.8541, right? So we're getting dialed into that number. So that's the sort of pattern that you're getting there in these numbers. Thought that was kind of interesting But definitely get more into the more into this kind of stuff in some other series as I put things together. But I thought I'd just make a quick video like this today and demonstrate this for everybody to kind of see and understand how this is all happening. Now the fine structure constant, this 137, we'll see how this shows up in the numbers later on as well. So this number, if we were to divide 1 by this number, this is that fine structure constant, right? That very subtle difference between the two sides of the coin, right, that enables all things, right? So that was discovered in like 1915 or something. But yeah, that would be a topic for another day. But yeah, that fine structure constant is going to be this number, right? Divided into 1, and that's sort of that delicate balance, right? That thing. So anyway, hope everybody enjoys this. I'll hope to get some more content out real soon. Thanks.